In section 8.2, we'll use the Bohr model of the atom to calculate the energies and wavelengths of electronic transitions. We'll do this specifically by applying the Bohr model to the hydrogen atom and using the Rydberg equation. Let's begin. Fireworks are an excellent demonstration of what happens to gas phase atoms that are heated. They emit light at very specific wavelengths, giving off the gorgeous colors we get to experience every summer during the 4th of July celebrations. This observation does not support the Rutherford model of the atom, which proposed that electrons could be found at any distance from the nucleus, which means atoms should be able to absorb light and emit light over a continuous range of energies. Niels Bohr proposed a different model of the atom to account for these observations. In the Bohr model, electrons are found in orbits at specific distances from the nucleus. These orbits are associated with discrete energy levels with a unique set of energy levels for every element. This is that spectral fingerprint we talked about in a previous lecture. While the Bohr model does offer some utility, note that this is not the current model of the atom. We'll discuss that model at the end of the semester. I mentioned previously that electrons travel in orbits that we call the ground state until they absorb light, moving to a higher energy orbit or excited state. When the electron eventually drops back down to the ground state, you'll see light emitted at the same wavelength that was absorbed. This light will be in the form of a photon. How many photons of light are emitted during these transitions? It depends on how the electron drops back down to the ground state. If an electron falls directly from the third level to the first level, 1 photon will be emitted. If, however, the electron falls to the second energy level, then falls again to the first energy level in this distinct two-step process, then we'll see 1 photon emitted for each electronic transmission. We can calculate the wavelength of light or energy emitted from these transitions using the Rydberg equation. The Rydberg equation is only valid for the hydrogen atom. We'll give the wavelength in meters and has 2 positive integers, N1 and N2, corresponding to the electronic energy levels in the atom. We can combine the 1 over lambda form of the Rydberg equation with our E equals hc over lambda equation to find the energy. Note that the Rydberg constant you use depends on the quantity you're calculating. When finding the wavelength, you'll use 1.097 times 10 to the 7th reciprocal meters, while calculating the energy requires the use of 2.179 times 10 to the negative 18th joules. Let's try an example problem. We're asked to calculate the emission wavelength of the photon emitted when an electron drops from the 4th energy level to the 3rd, then decide if this photon will be visible to the naked eye. To do this, we'll use the Rydberg equation 1 over lambda equals r sub h 1 over n1 squared minus 1 over n2 squared, using n2 equals 4 and n1 equals 3. Note that when calculating the wavelength, you always want to make sure the larger number is n2 and the smaller number is n1, so you'll get a positive result. Plugging these values in, we get 1 over lambda equals 1.097 times 10 to the 7th reciprocal meters. 1 over 3 squared minus 1 over 4 squared equals 5.333 times 10 to the 5th reciprocal meters. We're not quite done yet, so we'll take the reciprocal to get lambda equals 1.875 times 10 to the negative 6th meters, which we convert to nanometers. 1,875 nanometers is a longer wavelength than the 750 nanometer cutoff for visible light, so this means our light is in the infrared region. Using the same example, let's also calculate the energy associated with the transition. Plugging our values into the Rydberg equation, we see that the energy is 1.059 times 10 to the negative 19th joules. Energy levels have a general trend in spacing, where we observe that levels closer to the nucleus are spaced farther apart. The farther you get from the nucleus, the closer the energy levels become. This means that an electron dropping from the n equals 6 to the n equals 5 level will emit less energy and have a longer wavelength than an electron that drops from the 3rd to the 2nd energy level. Note that in both cases, a single photon is emitted. By convention, an electron removed from the atom is assigned an energy level of infinity and an energy of 0 joules. The lower energy levels are given a negative value as they must have less energy than an electron in the highest energy level, infinity. While the Rydberg equation only works for the hydrogen atom, if you check out the Flame Test Interactive or the Atomic Spectroscopy app in the textbook, you'll see that all atoms emit characteristic spectra corresponding to their unique arrangement of electrons. Finally, I'll leave you with the parting thoughts of the authors.